Hey everybody, we're back. Let's talk about a change in linear and exponential functions. So before we were talking about arithmetic and geometric sequences. So now we're going to see how they are similar to linear functions and exponential functions. So let's talk about what we've learned already. So we know that arithmetic sequences that we've already learned, and today we're going to learn how linear functions are similar to them. Okay, so we remember that a slope-intercept form of an equation can be y equals mx plus b. Well, I can just, because this is addition, I can rearrange this around because addition is commutative, and I can call this b plus mx. So again, this is the same equation, just moved around because we can add in any order. And then we can see now that here, we can see this looks like the arithmetic sequence initial value. So a sub o, our initial value, is like the starting value, the y-intercept, and d, the common difference times n, is very similar to mx because it's a rate of change, or that common difference times whatever interval we're looking at. So we know that this initial value on the left here is like saying, okay, that's like saying this is our a naught, or same as that y-intercept. And our constant rate of change for our arithmetic sequence is the common difference, or the slope. So these are where we are similar. Okay, so when we're not starting with the initial value, right, we use the kth term instead. So in that case, the arithmetic sequence would look like this. So remember, point slope form used to look like y minus y1 equals m times x minus x1. Well, if I if I move over to get this y by itself, I would get y1 plus m times x minus x1. Keep in mind, x stays the same as well. So this now, if we look at this and we analyze it, we can see, please use your highlighter, that this kth term value is the same as, hey, whatever this y1 value is, that y value of the first point. And that our slope here, remember we already said it's equivalent to that common difference. And this x is the same as this variable. And then x1 is the same value of how much from the initial value we started from. So we can see that there is a huge correlation between arithmetic sequences and linear functions. So for example here, if you've got the point x1 and y1 for a linear function, it's similar to k comma the kth term of an arithmetic sequence. So let's talk now about how exponential functions and geometric sequences are very similar, okay? So what do we know about an exponential function? Well, we know an exponential function, if you remember from before, that some value a times the base number raised to the exponent is an exponential function. We see that is really similar here to a is like saying the initial function, or the initial value. B is that base number, that's like our common ratio. And n is the same as our exponent, or your unknown value. So again, this is instead of r, this is instead of r, that common ratio. So when we're not starting with the initial value, we can transform the equations from above by using the kth term as well. So remember, from our geometric sequence, we saw this here, where we start with our kth term times the common ratio to the n minus k power, where you use k from the initial value. Well, in our shifted exponential notation, we know we can take y1 times r to the x minus x1 power. So again, this x and this n are the same idea because we're talking about them as the variable. where our kth value of g is the same as our y1 value. Our common ratio is here. And this is our distance from that initial value of x as well. So the point x1 comma y1 is similar to k comma kth term of the geometric sequence. So let's talk about what this would look like for its domain. So remember that the domain of a sequence will not be the same of the domain of the corresponding function. So remember that a sequence is distinct or discrete values, okay? So the domain of the sequence is discrete, meaning they're not values in between their specific points. Where the domain of the function on the right, we know we go from right to left, is every value or all real numbers from negative infinity to infinity. So this is the difference between the two, that their domains are different. Okay, so how can we recognize how to change the output value? So remember that when we were talking about linear functions and exponential functions can both be expressed analytically in terms of an initial value and a constant involved with change. So that was between the initial value and the kth value. There's a difference between the two, though. Linear functions are based on addition. This is crucial. Linear functions are based on addition, where exponential functions are based on multiplication. So it's really important that you see that, okay? So overall, over equal length input value intervals, the outputs of the function change this way. If it's linear, they're going to go at a constant rate. Okay, and that's because we're adding the slope every time. If we're talking about exponential, this is going at a proportional rate. That's that idea of the ratio. So we're multiplying the ratio and we're adding the slope. Okay, so let's look at this one. For number one, it says a function has the following coordinate points. Could the function represent a linear function, exponential, or neither? So what do we know here? So I see that the x's are increasing by 1 every time, so that's good. So let's look at what's happening to the y. The y value is increasing by 3, and then it's increasing more than 3. So we're increasing by 3, and then we're increasing by 12. So this tells me let's look at a non-additive way. Let's look, can we multiply? We can multiply by 4 every time. So this tells me that it's exponential. Okay, same thing here. 5, 6, 7, so x's are increasing by 1. So 3 to 7 is adding 4. 7 to 10 is adding 3. So what do we see here? Is this a linear? No, but it's also not multiplying the same number, so this is a neither. Okay, and then here, if I look here, 3 to 5 to 7, so this is adding 2 every time. So now if I look at this, are we adding the same amount or multiplying? So negative 1 to 7 is adding 8, and 7 to 15 is also adding 8. Because we're adding both time, is it adding the same amount? Yes, it is, so this is linear. So if we know a function is linear or exponential for sequences that are arithmetic or geometric, then you only need to know 2 distinct values to come up with an equation or the rule for the function sequence. So here's number 4. It's known that f of x is a linear function and that it passes through these 2 points. Write an equation for this function. Well, we know that the common difference is going to be the same as the slope. So we know the slope is going to be y2 minus y1, so 1 minus 7, and x2 minus x1 is 3 minus 8. We get 6 over negative 5. Well, we know this function is the slope times x minus x1, here's our x1, plus y1. And there's our function. We can also say that if you wanted to use our second point, you could say f of x is also negative 6/5 times x minus 8 plus 1 as well. Hey guys, so let's go ahead and talk about how do we do this on number 5. So it's known that the function is exponential. So remember f of x, if it's an exponential form, it looks like a times b to the x exponent. And it passes through these points 2, 5, and 4, 12. So if I were to write that like in terms of points or a sequence, right? So here's my first term, I don't know what my second term, let's plug that in here. My second term would be 5. My third term, I don't know, but my fourth term is 12, okay? But I do know it's exponential, which approximates a geometric. Okay, so we know we're looking for a constant ratio. So here's the deal. I don't know what this is here in that third term, but I know that 5 times the constant ratio is the third term, right? And then I know if I take that third term and I multiply it times r, I will get 12. So in other words, we're going to say, hey, if I take that third term and multiply it by the constant ratio, we will get 12. So this gives us an equation to find that constant ratio. So we get that this becomes 5r squared equals 12. Divide both sides by 5, and I end up with square root on both sides. We can just take the principal square root because exponential functions won't be negative. We get r equals the square root of 12 fifths. So there's my value for r. So in this case, when we're looking at this, we can see that instead of b, we can use r to the x power, which in this case is the root of 12 over 5. And we can choose two things. So number one, we know the second term is 5, and then this would be x minus 2 for the second term. Or if you wanted to use the fourth term, we could use 12 times r, sorry, this is the root, to the x minus 4 power. And that would give you a rule for either, okay? So number 6, it says the following functions are either linear or exponential. So linear or exponential, identify the constant, either slope or the ratio, that causes the output values to change. So here I can see really quickly that this is a geometric because it looks like a times b to the x, or a times r to the x power. So in this case, the constant is r equals 2, okay? So we have a ratio, or a common ratio of 2. And if we look here on number 5, our slope is 5. So we know that this is a slope of 5. Okay, for number 8 and 9, it says, which of the following are either linear or exponential? So now we're just analyzing DNA. So what do we know here? I'm going to look at the jumps from x. So I know from x, this is 4. From 7 to 11, that's adding 4 again. So if I'm looking, so what are we going to do if this is a arithmetic. So from 10 to 6, we subtract 4, and from 6 to 2, we subtract 4 again. This tells me that it's linear. And that's because as x changes for each input, so for each input change of 4, it has a constant rate of change, and that's negative 4. Okay, and then if I look here, from 1 to 3 is adding 2, from 3 to 5 is also adding 2, from 2 to 6 we would add 4, and from 6 to 18 it's not going to be adding 4. This is actually adding 12, so we know that this is not going to be linear. Let's see if it's geometric, okay? So from 2 to 6, if we multiply times 3, and then 6 times 3, we'd also multiply by 3. So we know that this has got to be exponential. And that's because for each input change, or delta, of positive 2, we have the function changes proportionally by a ratio of 3. All right, that's all we have this time. I'll see you back in class.